Assalamualaikum and greetings to Dr. Raja. Today, me and my partner Fatih Atira will present to you a case study entitled Metabolic Pathway to Hydrogen Production in Fermentative Acidogenic Microflora. Now, let's move on to the abstract of this study. Hydrogen gas or biohydrogen gas can be produced usually from wastewater using activated sludge through three major pathways, which are the breakdown of the pyruvic acid into acetyl-CoA, the oxidation of NADH to NAD+, and lastly through the hydrogen-producing acetogen bacteria. Even though there are a few approaches available for the production of the biohydrogen gas, there is no single approach that fits for all. In this study, specifically acclimated acidogenic microflora has been used and its ability to produce biogas was tested. After 68 hours of the incubation period, 247.7 ml of biohydrogen gas was produced, where 69 of the biogas was produced from the breakdown of the pyruvic acid, while another 31% was coming from the oxidation of the NADH. Hydrogen that coming from the acetogen bacteria was absent, maybe due to the acetogen itself does not functioning well under the given condition due to the hydraulic retention that was less than 8 hours. Biohydrogen gas was known for the most effective fuel due to its high energy content, greener energy conversion, and better efficiency and recyclability. Biohydrogen gas that was produced by the acidogenic bacteria was found to be the most environmentally friendly approach, as this process was less intensive and low power consumption compared to thermochemical and chemical processes. Production of biohydrogen gas through the fermentation also was claimed to be better than photosynthetic approach, as the rate of the production for the biohydrogen gas was much more faster. However, the final outcome for the trial scale production was not perfect due to the presence of the byproduct of the fermentation itself, which is alcohol. As for the methodology, the production of the biohydrogen gas was initiated with continuous stir tank reactor (CSTR) that was used to get specifically stabilized and acclimated acidogenic fermentative microbe community for the batch culture later. The temperature of the tank was set up to 35 degrees Celsius and sodium bicarbonate was added to maintain the pH value of 4.5 inside the reactor. Molasses or the substrate and the synthetic fertilizer containing nitrogen and phosphorus was added continuously for 8 hours. The biogas was produced, then will be collected in the water log and measured using gas meter. The reactor then will be inoculated with secondary sludge from wastewater plant treatment up to 40 days, resulting various liquid products being produced, indicating a mix of microbial community was developed in the CSTR tank. Some of the mixed culture from CSTR tank previously was transferred into the batch culture aluminum flask to investigate the hydrogen productivity with different substrate. 500 ml mixture of substrate that consists of ethanol, acetic acid, propionic acid, butyric acid, and valeric acid, and the mixed culture was maintained at 35 degrees Celsius in the rotary shaker water bath. Several essential minerals was added to meet the requirement growth of the mixed culture. The pH of the flask was maintained at 6, and the fermentation process was allowed to occur. Several parameter analysis such as pH value was measured using standard method. Glucose concentration was measured using sulfuric phenol method. 5 ml of sample from the batch fermentation was sampled for every 2 to 5 hours, filtered and injected into analyzer where the concentration of volatile fatty acid VFA and the ethanol fermentation is measured using gas chromatography. The biogas that was produced also measured using gas chromatography method.
Now, I will present the result of our study on hydrogen production in fermentative acidogenic microflora. The production of hydrogen firstly occurred within the first 36 hours of fermentation and ceased when the pH of the medium dropped to 3.2. During this period, the total gas produced amount to 480 ml per 100 ml of substrate, with hydrogen contributing to 247.7 ml. However, there was still a notable amount of residual glucose left in the medium, which is about 4.5 grams per liter, indicating that not all of the glucose was metabolized. In terms of fermentation byproducts, several key metabolites were detected. Ethanol was present at a concentration of 872 mg per liter, acetate at 432 mg per liter, butyrate at 433 mg per liter, and propionate at 530 mg per liter. Interestingly, when alternative substrates such as ethanol, propionate, and butyrate were tested, no hydrogen or acetate production was observed. This absence suggests that under the given experimental condition, the acetogenic pathways were inactive, either due to microbial inactivity or complete absence of hydrogen-producing acetogens. Based on the results, we were able to identify the dominant metabolic pathways responsible for hydrogen productions. The oxidative decarboxylation of pyruvate is the major route, which hydrogen yield at 69%. In this pathway, pyruvate is converted into acetyl-CoA and releasing format as a byproduct. This format is then split into hydrogen and carbon dioxide by the enzyme formate hydrogen lyase. The remaining 31% of hydrogen production was attributed to the NADH oxidation pathway. In this pathway, the NADH will carry its electron, which generated during glucose breakdown, to protons, resulting in the formation of hydrogen gas. This process is facilitated by hydrogenase enzyme and plays an essential role in maintaining the redox balance of the system. This study highlighted that the acetogenic pathway was inactive. Firstly, the hydraulic retention time HRT in the reactor was set at 8 hours, and acetogenic bacteria are known to be slow growing. This relatively short HRT likely did not provide sufficient time for them to establish and function effectively. Consequently, the faster growing acetogenic bacteria will dominate the system. Secondly, the high partial pressure of hydrogen within the reactor created unfavorable conditions for acetogenic reactions. These reactions are favorable only when the hydrogen levels are extremely low, which below 0.1 atmosphere. Since hydrogen was not removed or consumed during the process, it will accumulate and creating inhibitory condition for acetogens. Additionally, the fermentation profile supports this explanation. Instead of continuing to produce hydrogen, the microbial community will shift towards the generation of more reduced compounds such as ethanol. This metabolic shift helps the microbes maintain the redox equilibrium under condition where hydrogen removal is limited. In the conclusion, our study revealed that the oxidation decarboxylation of pyruvate was the primary metabolic pathway for hydrogen production. The NADH oxidation pathway also contributes significantly. The acetogenic pathway, which could potentially convert compounds like ethanol, propionate, and butyrate into acetate and hydrogen, remain inactive under the tested condition. This is due to the short hydraulic retention time and the high hydrogen partial pressure within the reactor. These findings underscore the importance of reactor conditions like HRT, pH, and also hydrogen pressure. From a practical perspective, this study contributes valuable insights for the design and optimization of hydrogen-producing bioreactors. By understanding which pathway dominate under specific conditions, we can make adjustments to either promote faster hydrogen production routes, such as the NADH pathway, or create favorable conditions for acetogen when necessary. That's all from us. Thank you so much for your attention.